Among the lesser-known innovations of the Cold War are the survival tools developed for regions so remote, so hostile, and so cold that normal equipment simply could not function. The Arctic was one of those places. Navigation crews, radar operators, weather teams, and long-range reconnaissance patrols worked in conditions where batteries froze solid, gasoline thickened into sludge, and generators either failed or were too loud and risky to operate near sensitive sites. So Cold War engineers created a device that produced power reliably in the brutal cold without requiring batteries, liquid fuel, or even sunlight. It became one of the quiet workhorses of Arctic operations, and it still works today because it is based on a principle older than electricity itself. This device was the thermoelectric generator, specifically the Cold War field versions designed to turn temperature differences into usable electrical power. Before diving into how these generators worked, it's important to understand the problem they solved. The Arctic wasn't just cold, it was an environment that defeated traditional electronics. Battery chemistry slows dramatically as temperatures fall. A standard field radio battery that might last a full day in mild climates would die in minutes in -40 degrees Celsius conditions. This created an operational vulnerability, especially for early warning stations and remote outposts meant to detect Soviet activity. If communication failed because a battery froze, the entire chain of defense could collapse. Solar power wasn't an option, since Arctic winter brings weeks or months of darkness. Gasoline generators required constant maintenance, spare parts and fuel, which often couldn't be delivered reliably. Thermoelectric generators filled the gap, simple, silent, and entirely independent of weather. Cold War power generation in the Arctic relied on thermoelectricity and extreme temperature differences. Thermoelectric generators operate on the Seebeck effect, where electric current is produced when two different conductive materials experience a temperature difference. In Cold War field units, the hot side was created using a small chemical fuel or heat source, while the cold side was provided by the freezing external environment. The greater the temperature difference, the more electricity the device produced. This turned Arctic weather from a liability into an asset. Instead of fighting the cold, engineers used it as part of the system. Soldiers and technicians could set the device on the ground, ignite the heat source internally, and allow the frigid outside air to cool the opposite plate. Even in extreme cold, the units produced enough power for radios, navigation equipment, small lamps, and battery recharging. The design was rugged, quiet, and dependable. Everything needed for isolated positions. This device allowed Arctic teams to maintain communication even when every other system failed. Communication was the lifeline for Cold War operations. Missile detection networks, research teams, and reconnaissance groups depended on radios that could not go silent. Thermoelectric generators kept those radios running hour after hour. Unlike wind turbines, they did not require moving parts that could jam with ice. Unlike solar panels, they didn't depend on clear skies. Unlike combustion generators, they didn't alert enemies with noise or exhaust. They were particularly valuable for early warning radar stations across Alaska, Greenland, and northern Canada, where teams rotated through small outposts exposed to storms, ice, and polar night. In many recorded incidents, these generators provided the only dependable source of power when blizzards knocked out larger systems. Their reliability earned them a place in aircraft survival kits as well, ensuring that downed pilots could signal for help even in multi-day storms. You can actually apply this Cold War principle today to create off-grid power in, some of the most extreme conditions. Modern thermoelectric modules are widely available now and, they rely on the exact same physics as those Cold War originals. To create a field-ready version, all you really need is a heat source, something like a camping stove, a candle, or even just a hot metal plate, and a cold sink, such as snow, ice, rock, or, say, Arctic air. By placing a thermoelectric plate between the heat and the cold, you create a voltage. If you wire that through a regulator, it can charge a battery bank, run a small radio, or power LED lights. A practical approach often involves mounting the plate to a metal cup or pot that sits over a small flame, while the opposite side is exposed to the cold air. The stronger the temperature difference, the more wattage you actually get. In winter conditions, this method often outperforms many battery-based systems, simply because the cold actually improves the device's efficiency. For shelters, you can mount a thermoelectric plate to the side of a wood stove and route the cold side outdoors. This produces power for as long as the stove is burning. Understanding why this device works so well really reinforces some foundational survival principles. Cold weather can absolutely punish equipment that relies on chemical reactions, fuel vaporization, or lubricated moving parts. The brilliance of thermoelectric systems is that, they bypass all those weaknesses entirely. They convert heat to electricity through solid-state physics alone. No gears, no pistons, no oil, no batteries, no starter motors, none of that. This makes them, frankly, a model of what survival equipment ought to be: simple, durable, and predictable. Their reliability during the Cold War teaches modern preppers and field workers an important lesson. The best equipment in extreme conditions is not always the most advanced one, but the one least vulnerable to failure. When you study Cold War equipment, you'll see this pattern repeating itself across heating systems, communication setups, and even rations. This Cold War device is still relevant because, quite simply, Arctic challenges remain unchanged. Today, expedition teams, winter researchers, remote cabin owners, and bush pilots still use thermoelectric systems. They are, in fact, a staple in polar survival kits and long-term off-grid setups. Some modern variants attach directly to camp stoves and cookpots, producing electricity while heating food. Others clamp to wood stoves in remote cabins. A few experimental systems even integrate with rocket stoves for winter survival scenarios. What makes this technology truly timeless is its independence from modern supply chains. As long as you can produce heat, whether it's from wood, alcohol, fuel tablets, or even just a candle, you can produce power. The thermoelectric generator stands as one of the most durable examples of Cold War practicality. It was never glamorous, yet it was trusted in one of the harshest environments on the planet. It turned cold into an advantage and provided power when everything else simply froze. For serious history enthusiasts and survival-minded viewers, understanding this device is more than just a lesson in Cold War engineering. It's a reminder that ingenuity so often comes from solving the most basic human needs in the most unforgiving circumstances. If you value deep dives into forgotten Cold War tools like this, do consider subscribing, sharing the video, and adding your thoughts in the comments. There are, honestly, many more pieces of overlooked survival history worth exploring, and your support helps bring them forward.